So let's look today at diffraction. Yesterday we talked about interference. Back to our particle wave debate. Remember Newton, light travels in straight lines. Straight lines create sharp shadows. So you might have a picture that looks like this. If you have a light source and you have a wide window, you're going to get a shadow with nice sharp crisp lines. Now Huygens and Fresnel, who were our authors of the wave theory, said that light can bend around objects just as sound and water do. So their picture of a shadow might look something like this, although notice that you only get that kind of interference pattern over here, this bright, dark, bright, when you have a very narrow slit. So you don't get that sharp pattern. Well, diffraction is a wave phenomenon that's well understood, and this is like a picture from above. You can see some water waves coming in. You have an opening between the rocks, and you see that the water waves kind of spread out in sort of a circular, semicircular form. That's diffraction. That's something that waves do. So it's observable when the wavelength of the wave, okay, is on the same order of magnitude as the opening or the through which it's going, so depending on the obstruction. So on this particular case, it looks like the wavelength is about 1/5 the size of the opening. So about the opening is 5 times one wavelength. If you had much shorter, crisper, smaller waves, then you can imagine that the waves would come straight through, creating, like a sharp shadow. So the waves would come straight through like this. They wouldn't bend like they do. But because the wavelength is on the order of the opening, then you'd get this bending effect. So that's something that is observed with water. Now let's see what we can figure out what happens when it comes to light. All right, so here's the principle again. So remember Huygens' concept of waves and little wavelets, that as a wavefront approaches an obstruction, and here's your obstruction, then at the corner right here, think of that as one little wavelet. That's going to create a little arcing wave. And so that wave will create a wave, which is going to create another wave over here, and you're going to get this sort of bending around your obstruction. That's the notion of diffraction. If you have a small obstruction in front of wavelengths, you're going to get this bending around it until eventually that little blockage is going to be minimized. Now, in this case over here, where the wavelength is very small compared to the size of the obstruction, then you get a really nice sharp shadow. So that's what Newton would have speculated, that light only travels in straight lines. But according to Huygens, it doesn't. It just appears to travel in straight lines because the wavelength of light is so small compared to most of the obstructions of the experiments they've been looking at. So here are some photographs of waves. The first one on the left, again, you have a small opening. Looks like the opening is about the order of magnitude of the wavelength. So here's the wavelength right here, and here's the opening right there, about the same size. You get a great example of diffraction going on. Another one over here. So if you think about sound, if you're at a concert, if there's a sound source and you have a wavelength of sound coming out towards you, if you plant yourself right behind a beam, so you have the worst seat in the house, you're not going to be able to see the performer on stage because light is going to travel right past you and not bend around that obstruction because the wavelength of light is so small. But the wavelength of sound is much larger, and so that wavelength is going to bend right around the obstruction, and you'll be able to hear. You might not be able to hear it quite as well as if you didn't have the obstruction, but you'd still be able to hear because the sound waves will travel right around the obstruction. In fact, if you're standing outside the door, so if you're propped out here outside the door, outside the concert hall, you're still going to be able to hear the concert because the wave pokes through and then it bends around the corner. So you are getting the sound bending. Long wavelengths are going to bend around small obstructions. Short wavelengths are going to bang right into them and create a big shadow effect. So radio and TV waves, think about what happens with those. I don't know if you've ever played around driving, but can you pick up more easily if you're in a city with lots of tall buildings? Can you pick up better AM or FM? Well, it turns out that in a city, longer wavelengths can move right around the buildings, but the shorter wavelengths get blocked, like in a shadow fashion. So if you have really short wavelengths, when they hit a building, they get blocked, and if you're standing behind a building, you'll be in the shadow of the wave, and you won't be able to pick up the FM reception. The AM reception, though, okay, those are, remember FM was megahertz, and the AM waves are longer, so those are going to bend right around the building. So if you are in a bunch of buildings, you can still pick up your AM reception because that longer wavelength is going to bend right around those buildings. So, in 1818, August Fresnel, remember it was 1802 that we had the Young's double slit experiment, and Huygens had long since died, but Fresnel wrote a paper on diffraction, and he proposed that if light, that light in fact does diffract. And another scientist named Simon Poisson was very critical of his paper and theory and said that it's an absurd prediction that light would diffract, and he said that if in fact you shined a light and you shine it around a small object, then behind the small circular object, a little bright spot would appear. And he said that's ridiculous. Of course that would never happen. So, as soon as you say it can't be true, somebody has to try it out. And that experiment was Dominique Arago, who conducted the experiment with a penny and a light and shined it, had it diffract, and created right in the center there a bright spot. So he had proved Fresnel's paper and his idea of diffraction. That spot is now famously described as the Poisson spot, after the scientist who thought that it would be absurd to think that it could ever happen. So we can look at demo wavetable. We'll do that in class later. Okay, so quick recollection of interference and why we have interference. Remember, if you had two different slits and the distance traveled was different for each particular wave, then if there was a one wavelength difference, you're going to get constructive interference. If you have a half wavelength difference, you'll get destructive interference. Well, now let's think about what's happening with diffraction. Now we don't have two slits, we just have one opening. So here's our opening over here. And we have these waves coming in and they're hitting this opening. Well, if you think in like Huygens, that each little spot is a wavelet source, then you could think of how waves might be initiating up here. And they're going to travel out in all directions. So they're going to go this way, and they're going to go that way. So you could think of one wave initiating from right here, and then you could think of another wave initiating from, I should do that purple, shouldn't I? Let's do purple. So it was a purple wave initiating from right here, and it can travel up. And then you could have a third wave down here that's initiating down here. So within one opening, you have all these three little tiny waves. You have, infinitely many waves that are actually originating from there. But if you think of those three separately, then you say, well, if the wave coming from here constructively interferes with the wave coming from here, you could get a bright spot. Or you might have it destructively interfere and get a dark spot. And in fact, what we observe, if you're shining light through a small opening, you get these bright spots and dark spots. So the bright spot in the center, where you're going to have essentially no interference, nothing is there to cancel out, the light's going straight through. But then on the outer edges, you're going to get little dark spots of interference, where the wave from one portion of the wave came up and it destructively interfered and canceled out the wave from another section. So you get little dark spots. So that's the idea behind diffraction. With diffraction, you're going to get a central bright maximum, but you're also going to get these minima. So it's brighter, much brighter in the middle, and then as you get further away, it drops off very quickly. So the pattern for interference is slightly different. The diffraction has a much higher maximum in the middle. But the geometry is the same idea. Where you get destructive interference, you're going to get cancellation, you're going to get a dark spot. If you take a whole bunch of spots, a whole bunch of openings, and you overlap them, so 1, 2, 3, 4, you have a whole bunch of openings, and then you bring in your light sources, then the light that travels through one opening might overlap with the light coming from another. And if those two lights are going to overlap, you can get constructive interference or destructive interference. And so you're going to get these fringe color patterns of bright different colors. So you get white in the middle as everything just travels through, and then further out you're going to get a red band and a yellow band and a blue band. A diffraction grating is where we have lots of openings through which light will pass, and then we can observe the pattern on the opposite side. The more slits you have, the more distinct these bright spots become, and we will check that when we do our lab next week. So if you have a diffraction grating, the good news is you can use the same formula. The mathematics are slightly different, but the formula ends up being identical. So d sine theta represents, the d in this case is not the distance between the slits, but it's the distance of the opening. So if you have an, let me make it more like an opening. So if you have an opening here, then d represents the width of that opening. So d has a different meaning than it did with the two-slit interference. D was the distance between the slits for interference, but for diffraction, it's the opening width is equal to m lambda, and you're going to get these same ideas of bright spots and dark spots. M equals 0 being the the highest maximum order in the middle, and then you can go above and below. With the diffraction grating, often it'll say grating has 150 lines per meter. They're usually etched with lasers, so you can get this 150 lines per meter. Well, the question is, well, then how big is one opening? If you have 150 lines in 1 meter, well, then basically what you're going to do is take the inverse of that, and so, oops, back up, sorry. So the inverse of that is 1 over 150,000, and that's, I don't even know what that is, but it's a small, small number. So d tends to be very, very small when you're talking about diffraction gratings. So here's an example problem that we can work out together. Diffraction grating has 4,525 lines per centimeter. It's illuminated by direct sunlight. The first order solar spectrum is spread onto a white screen hanging on a wall opposite the grating. At what angle does the first order maximum for blue light with a wavelength of 422 nanometers appear? So where are we going to see the first blue light on our diffraction spectrum? All right, so let's look at what we know. We've got blue light. We're talking white light coming in, but we're going to be isolating just the blue part. All right, so here we go. 445.25 lines per centimeter. We're going to convert that. We need to get a distance for d. That d sine theta equals m lambda. We need d. How open is one little opening in this diffraction grating? So we say, well, 425 lines per centimeter times 100 centimeters per meter is 452,500 lines per meter. Or if you flip that over, that's 1 meter per 452,500 lines, which is 2.21 times 10 to the minus 6 meters per line. And that is your d, okay, your meters. That's how big your little opening is. It's teeny, teeny, tiny, okay? So that's your d for your d sine theta equals m lambda. So blue light, we're talking about 422 times 10 to the 9th meters, or 422 nanometers, okay? That's the wavelength of the light. D sine theta, okay, d sine theta is m lambda. So we want the first order. So in that case, m equals 1, because that's going to be out of the center. You don't want the bright spot in the center. You want the first one off to the right or above or wherever. Okay, so d is going to be 2.21 times 10 to the minus 6. M is 1. Lambda is 422 times 10 to the minus 9th, and you can solve for sine theta. Sine theta is 0.191, therefore theta is 11 degrees. So you can measure 11 degrees away, and that's going to be your first blue line. One issue you do have with diffraction, if you're trying to observe something through a small opening, if you have two distinct sources, then the overlapping patterns of coming through a slit, so for example you have this problem when you're looking at a telescope. Your eyeball has this problem. If you have two distinct sources, the pattern or the image on the back of your retina or in the back of the telescope could overlap. And so you're not going to get a distinct look at two bright spots. They're going to be kind of overlapping. So here's an example of what happens. And this is straight out of your textbook. That's where this picture comes from. 2 point sources are barely resolved. So you have like they come mushed together. It becomes one sort of image instead of seeing two dots. And this happens with stars. If you're looking at stars, if the aperture of your telescope isn't large enough, then you can't discern that they are two separate stars. They seem to be squished together. You can overcome that effect by having a larger aperture opening. Think about, a small slit, you get diffraction. If you have a bigger opening, you're going to get less diffraction, better resolution, and those two objects are going to be separated so you can see them. Kind of another cool effect, thin film interference. Okay, so if you have a thin film, so you'll see this like in a puddle. Sometimes after it rains in a puddle, there'll be a little bit of oil in the top of a puddle, and you'll see a pretty little rainbow. Well, what's happening there? So you have incident light coming in, and incident light is going to be all wavelengths of light, and it comes in and it hits at an angle. It goes from air to oil, and of course it's going to refract. Some of the light, though, is going to reflect. Okay, so it bends, or it reflects back. So certain wavelengths are going to reflect back. And if it turns out that the thickness of the oil, so the thin sheet of oil, the thickness of the oil is just right that it happens to be a multiple of the wavelength of a given frequency of light. Okay, so let's say red light. Okay, so if it's like an exact multiple, like maybe 2 wavelengths or 3 wavelengths or 10 wavelengths, then the light that hits through, comes through, and bends back, bounces back, when it releases and refracts again out into the air, if that has traveled a distance that happens to be a multiple of the wavelengths, then you're going to get constructive interference. So that red light is going to overlap. So if it's just the right thickness, then red is going to be appearing. And that's what you're observing when you see these rainbows on bubbles. You have this what's called thin film interference, and it has to do with light going from air into oil or water, bouncing back and coming back out and interfering with the original reflection. So the reflected light interferes with the refracted and refracted light, and when they overlap, you get constructive interference of given wavelengths, so you get these beautiful color spectra. And that concludes our lecture for today.